Imagine looking into a mirror that doesn't just bounce back your reflection, but one that bends light, memory, and time itself. Not a mirror showing your face, but one showing the universe's first fragile breaths, when matter, energy, and space were still learning how to exist. That is the role the James Webb Space Telescope was built to fulfill. To look not at what is, but at what was. To peer into the dawn of everything. But when Webb's golden mirrors opened and caught light that had traveled for over 13 billion years, what it revealed was not a nursery of simplicity. It was not the expected cradle of scattered hydrogen clouds, faint flickers of baby stars, or chaotic fragments awaiting gravity's slow touch. What it revealed was something far stranger, a contradiction so sharp it cut through the very skeleton of modern physics. For decades, the story of cosmic evolution seemed stable, even comforting in its order. The Big Bang ignited the universe. A long dark age followed, a silence broken only after hundreds of millions of years when gravity finally coaxed matter into stars. Those stars formed in isolation at first, before joining into primitive galaxies. Over billions of years, these structures grew into spirals, clusters, and vast cosmic webs, eventually leading to planets, atmospheres, and the spark of life. That was the map, the progression. Simplicity to complexity. Nothing should shortcut the sequence. But Webb showed something else entirely. In a supposedly quiet region of sky, one of those endless black stretches where astronomers expected only emptiness, the telescope instead captured an image that overturned this narrative. It was a galaxy, fully formed, rotating, with spiral arms glowing like ribbons of starlight. Not a vague blur. Not scattered gas. A galaxy with shape, symmetry, and an active core radiating immense energy. And this was not an isolated finding. As Webb collected more light, more galaxies stepped out of the shadows, dozens of them, perhaps hundreds. And each one shared the same impossible quality, maturity. They weren't half-built structures clumping together from cosmic dust. They were stable, thriving galaxies far too complex for their place in the timeline. It was as if the universe had pressed fast forward on evolution, skipping billions of years and landing in an era that shouldn't exist yet. That's when a single question began to echo with unsettling weight. What if everything we thought we knew about the beginning was wrong? To understand the magnitude of this problem, we need to revisit how galaxies are supposed to form. In the aftermath of the Big Bang, matter was thinly scattered across space, mostly hydrogen and helium. Gravity acted slowly, pulling clumps together, creating stars. Those stars eventually clustered into the first galaxies, rough and irregular, nothing like the spirals we see today. This process takes hundreds of millions of years just to begin, and billions before galaxies achieve balance and elegance. But what Webb saw in those ancient photons defied this timeline. These galaxies weren't stumbling into existence, they were already thriving. Their rotation patterns, their star clusters, their very chemistry spoke of age, of cycles already complete. It was the astrophysical equivalent of finding a towering oak tree growing fully formed in a forest where the soil was laid down only yesterday. The chemical evidence was even more shocking. By analyzing spectral fingerprints, the unique patterns of light that reveal what elements are present, scientists discovered traces of oxygen, carbon, and even iron. These are not primordial ingredients. They don't emerge from the Big Bang. They are forged in the cores of massive stars and spread across the universe when those stars explode as supernovae. This process requires time. Generations of stars must live, die, and scatter their ashes into the cosmic winds before new stars and planets inherit these heavier elements. And yet, here they were. Galaxies less than 400 million years after the Big Bang already bore the marks of multiple stellar generations. That would mean the first stars had not only formed and died but that the cycle of birth and death had already repeated more than once. The early universe wasn't crawling, it was sprinting, burning, exploding, recycling, as if it were in a race against its own clock. The implications are staggering. These are not just the seeds of stars. They are the foundations of planets, atmospheres, and potentially life. To discover them so early is like finding a coral reef thriving at the base of a volcano that only erupted yesterday. The timeline doesn't just feel compressed. It feels broken. But then came the most outrageous discovery of all. Nestled in the heart of one of these young galaxies was a black hole so massive it dwarfed imagination. Over 1 billion times the mass of our Sun. Even in today's universe, such giants are rare. But in the early universe, their existence borders on the impossible. According to standard models, black holes are born when massive stars collapse. Over time, they grow by consuming gas, dust, and other stars, or by merging with one another. Even with the fastest feeding models imaginable, reaching billions of solar masses would take billions of years. But this black hole was already there, fully grown, within a few 100 million years after the Big Bang. It was as though it hadn't grown at all, it had arrived. To explain this, astronomers have turned to radical theories. Some propose that primordial black holes could have formed directly from the violent density fluctuations in the first moments of creation, bypassing stellar birth entirely. Others suggest that dark matter, normally thought of as a passive gravitational glue, may have played a far more active role, accelerating collapse and growth. These aren't tweaks to existing models. They are new frameworks, new rules for reality itself. As Webb continued sending back data, the strangeness deepened. Patterns began to emerge, not in the galaxies themselves, but in how they were arranged across space. Advanced algorithms revealed that their distributions followed a repeating mathematical ratio, eerily close to the golden spiral, the same ratio that appears in seashells, sunflower seeds, and hurricanes. This wasn't randomness. It was order. A fractal geometry embedded into the universe itself, stretching across scales of billions of light years. Was this simply a deeper law of physics at play? Or was it something more unsettling, a sign of intentional design hidden in the fabric of spacetime? The discoveries didn't end there. In a region thought to be barren, Webb's instruments detected something that sent a chill through the scientific world. Complex organic molecules adrift in space. Not just methane or ammonia, but polycyclic aromatic hydrocarbons, the chemical scaffolding of amino acids. The foundations of life itself. And they weren't tied to planets or stars. They were free-floating, ancient, and intact after more than 13 billion years. This suggested that life's ingredients weren't a late arrival. They were present from the beginning, seeded into the very structure of the cosmos. If that is true, life is not an accident of planetary chemistry. It is a cosmic constant, a thread woven into the tapestry of reality. Then came the most haunting image of all. Deep in a cluster of ancient galaxies, Webb captured a formation so precise it seemed sculpted. 6 galaxies arranged in a perfect circle around a central object, each evenly spaced, orbiting in harmony like petals of a flower. No natural model could reproduce such symmetry. Astronomers debated explanations, gravitational lensing, statistical flukes, turbulence in the early cosmos. But none of them fit. To some, it looked less like coincidence and more like choreography. A structure waiting patiently to be seen, perhaps even a message written across time. And yet, even this was not the final twist. Some researchers began to whisper about something even stranger. The possibility that by observing the early universe with such clarity, Webb itself may be influencing what it sees. In quantum mechanics, the act of observation can alter the behavior of particles. But what if that principle scales upward? What if the universe itself, at its deepest levels, responds to being observed? There are hints, subtle and controversial. Images that appeared to shift when analyzed differently, data that resists being locked down, patterns that emerge only after repeated attention. If true, it would mean humanity is not a distant spectator of the cosmos. We are participants, co-authors of the very reality we study. What the James Webb Space Telescope revealed was never just about distant stars or swirling gas. It was about truth, an ancient truth too vast, too intricate, and too unsettling to be ignored. Galaxies too mature, black holes too massive, elements too advanced, patterns too precise, molecules too alive. Each discovery bending the timeline, breaking the rules, and whispering that maybe we have misunderstood the very foundations of existence. Perhaps the universe is not a story unfolding from simplicity into complexity. Perhaps complexity was there from the beginning. Perhaps the cosmos was never silent. Perhaps it has been waiting for us. Maybe Webb didn't just look back in time. Maybe it awakened something timeless. A memory. A pattern. A presence. And maybe, just maybe, that presence noticed us. So now the question isn't simply, what did Webb see? The deeper, more chilling question is, what saw Webb?